Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to discuss the solution to this MyMathLab problem. By the way, in my class, we're using the Thomas Calculus with Early Transcendentals, and this is Chapter 3, Section 3, Item 71. Find the value of a that makes the following function differentiable for all values of x. Okay, so what does differentiable mean? Well, differentiable means that the derivative exists. Let's take a look at an example of a value of a that I just randomly picked, the value 2. So we have g of x equals 2x if a is less than 0, or x squared minus 17x if x is greater than or equal to 0. What would that look like? And I used this website called desmos.com. It's a great website. And you can go there and use it as a free graphing calculator. So what we see here is on the right, we have the parabola portion of the piecewise defined function, x squared minus 17x. It would continue up here, and we'd see a red line going up through the origin. But remember, our piecewise defined function says it's only equal to that when x is greater than or equal to 0, so to the right of the origin. And then on the left, if that part of g is 2x, the blue line here would represent what that piece of the function looks like. Okay, so derivatives are slope, the slope of the tangent line. The slope of this line on the left is 2 everywhere. We know that because we're very familiar with slopes of lines. On the right, we would have to get a formula for the slope, which would vary depending on the value of x. But I can tell, looking at this graph, that it definitely would not have a slope of 2 right near 0. In fact, this red portion of the graph is going downward, so that would have a negative slope, right? So the slope on the left does not equal the slope coming in from the right. And since we're talking about differentiability or the derivative existing, we have a problem. In fact, anytime you have a sharp point in a graph, we do not have differentiability at that point. Even though the graph is continuous, it's not differentiable because it comes to a sharp point and the limit of the difference quotient, in other words, the derivative on the left, the slope, does not equal the derivative on the right. Okay, so let's suppose that we changed this a bit. As I mentioned, the red here, it has, the red graph has a negative slope. So let's say we change that to -2. Okay, so you can see that it's still not quite matching up. It would need to be something a little bit steeper, maybe -4. Oh, not quite. Okay, so maybe -6. Nope, keep going. Okay, and of course this is just going to be an estimate anyway. -8 still has a bit of a sharp point there. -10. Okay, we're getting very close. So in the neighborhood of -10 is where we'd expect our value of a to be. Okay, so analytically, let's go back to our problem and work it out. What we need is the derivative of this line portion, the y equals ax portion, to equal the derivative of the parabola portion. So I'm going to start with the portion of the function y equals ax. Well, we know that dy dx is going to be a for any value of x. Now we're only going to be looking at x values less than 0, but it doesn't matter. For a line, the derivative is the same everywhere. It's going to be just a. Now for values of x greater than or equal to 0, we're looking at the function y equals x squared minus 17x. And we've learned the power rule, and we can take the derivative of this function, dy dx equals 2x minus 17, right? Bring the power up front, subtract 1 from it, so we have 2x to the first power. The derivative of a constant times x is just a constant. So we don't have to write the power of 1 though, so let's erase that, okay. So what we have here is that the derivative is going to be 2x minus 17 coming on the right side of the origin. And on the left side of the origin, it's going to be whatever a is. This is asking us for what values of a would we have differentiability for all values of x, but really on this piecewise defined function, the line is nice and smooth and differentiable. All polynomials are differentiable everywhere. Okay, but we have two polynomials butting up against each other at x equals 0. So the only potential problem is what's happening at x equals 0. So what would the derivative be if I evaluated it at x equals 0? Well, for the right side of the function, we would have 2 times 0 minus 17 is negative 17 would be the slope of that parabola right as it hits 0. And so we need for our derivative on the left to also have a value of negative 17. So we need a to equal negative 17. So let's go back to our Desmos.com graph. Okay, and instead of negative 10 here, I'm going to put in negative 17. Oh, and look, it almost looks like a parabola. If you didn't know that this portion here was a line, and that it doesn't have that roundness to it that the parabola should have, it almost looks like a parabola. It looks seamless, in other words. And the reason is because the slope on the left here is negative 17 on the blue portion. And on the right, it's negative 17 right as it reaches 0. Of course, it's slightly different when x is 0.0001 or 0.002 or 0.5 or whatever. But right as it hits 0, it has exactly the same slope, and so it seamlessly flows into the line negative 17x. So in general, when you're given a piecewise defined function with two polynomial segments so that we know that each of those is continuous and differentiable everywhere, all you need to do is find the derivative of each piece, evaluate it at the point where they meet, the break point in the graph, and then set them equal to each other to find out what this missing value would have to be to guarantee differentiability. I hope you found this video useful. If you did, please remember to give it a thumbs up and like it so it helps other students to find the video.